Moving on now, though, our other measure of disease occurrence that is incredibly important is incidence. Incidence is also known as risk. So you can use the words incidence, risk, or also likelihood of getting disease. Those are synonymous, and we'll work more through with the language. So incidence is the occurrence of new cases of diseases that developed over a specified time period in a population. Okay, prevalence versus incidence. Fundamental knowledge in epi. Prevalence is snapshot in time. Again, you don't care when the person got the health outcome. If they have it at the point or the period that you are interested, they are counted. They are in your numerator. Incidence is about new cases. How many cases are being diagnosed? How many cases are developing? It's all about the new cases, not the ones that exist. So let's just go through our highlighted words here. So new cases. So people who are disease-free at the start of your watching them. This is sometimes really difficult to discern. Say you look at a population and especially for diseases that have sort of preclinical phases that aren't easy to detect. It's difficult to know who's a new case. But the idea with incidence here is that we're watching a population over time, and we're ideally able to distinguish who was disease-free when we started watching them and how many new cases arose over the period you're watching them. So time period, our other highlighted important term here, is, as I was saying, individuals are monitored over a specific period of time. Again, it's not a snapshot in time at one point like prevalence. We are watching and seeing how cases of disease occurrence occur as time passes. And finally, the last highlighted piece to be aware of in this definition is population. Now, we talked about population last time in the last video. Here, I'm going to put one new addition to the idea of population. To calculate incidence, to understand incidence, we need to know the individuals who are at risk of getting the disease. Now, this concept trips up students quite a bit because we talk a lot about, are you at risk for whatever it is? We actually mean something slightly different than the common language. So what do I mean at risk? That your denominator needs to be, well, you'll see, your denominator needs to be at risk. So what we mean in this sense is that at risk means those that have the potential to get the outcome. People are not at risk for outcome if they already have the outcome, right? So, and this is true primarily for diseases that can't reoccur. So if someone has already been diagnosed with type 2 diabetes, they're not going to get re-diagnosed. Or let's say even more clearly, type 1 diabetes, right? Once you have it, you have it. So if there's someone in your population when you are starting this period of watching them over time who already has type 1 diabetes, they're out, right? They're never at risk for developing type 1 diabetes. So you wouldn't watch them to see if they develop type 1 diabetes. It doesn't make any sense. Another one is they can't physically get the disease. So say your disease or your health outcome of interest is breast cancer. Or actually, I'm going to change it from breast cancer. What if it's ovarian cancer? Men cannot get ovarian cancer, except potentially in a few cases where someone's biologically male, but we'll ignore that for now. So you would never watch a population of men to see how many cases of breast cancer arose. Men, biological men, are not at risk for ovarian cancer. Third, they're immune to a disease. This is this is not always so clear cut, right? When we have vaccinations that don't necessarily make us immune. But imagine there was a disease where once you got it, you were 100% immune. You could not get reinfected. You should not be watching those people to see if cases occur. So they should not be part of your population at risk when you're looking at the outcome of that disease. And then finally, they cannot meet the definition of a disease. So, for example, SIDS, sudden infant death syndrome. The definition of SIDS is death among, unexplained deaths among children 1 year or younger, or before their first birthday. So you would never include children older than 1 year in your population at risk for SIDS. They don't go into your denominator as at risk. So the way I like to think about this, and I keep referring to your denominator, I like to think of if you think, and we're going to skip ahead to I'll show you the formula in a second, but I like to think of you have your entire population at risk and they meet these criteria. Again, let's say for ovarian cancer. Which ones are going to arise? Can your case of ovarian cancer arise from your pool of people at risk for that outcome? If there can never be someone who could potentially get the disease, whether it's based on their immunity status, their biological being, their characteristic like age, then they should not be in your population at risk. Okay, so now that we have an understanding of what we mean by population at risk, we're going to move into our two measures of incidence, cumulative incidence and incidence rate. And you'll see in a minute why we actually need two different ways to measure incidence. So let's start, wrong direction. Let's start with cumulative incidence. And this is the measure that I think you guys are probably starting to picture in your head as I'm talking about number of new cases and population at risk. In a lot of ways, this is sort of a simpler, more straightforward measure of incidence. So cumulative incidence, the definition or the formula is the number of new cases divided by the number of persons in the population at risk at the start of the observation period. So this is everything we've been talking about. So to assess cumulative incidence or assess incidence, as I mentioned before, you're going to need to follow a population over time, right? Because you need to be able to measure as new cases of an outcome exist. So again, imagine you're starting to watch a group of people. Say you're starting to watch in 2015, January 1, 2015, the population of Philadelphia. And then you're able to track them over time to see the new cases as they arise. So your numerator will be the number of new cases that arose, let's say, after 1 year. And your denominator will be the number of persons in the population at risk. Again, so we need to be able to determine who had the potential to become a case as they're part of our population at risk at the start of that observation period. So let's say the population of Philadelphia on January 1st. Okay, so there's our definition. Some things to consider. Cumulative incidence assumes a stationary population. All right, go back to the video before this and think again about a stationary population. It assumes that we have a complete population at the start of our tracking period, that no one, whoever's in our study or in our viewing tracking is in, and it assumes that we have followed them in the case that we're sort of talking about over the period of 1 year, over our full observation period. With the idea being that, we didn't get people who we couldn't find anymore. We didn't get people moving out. We have complete information about how many people from our population developed our outcome, became a case, essentially moved up to our numerator. And we know that we have full information about we have enumerated our entire population, if you want a fancy word. Okay, so we have assumed we have a stationary population that we have observed for the entire period of time. Now, as you can imagine, the longer this time period, the more this assumption becomes a problem, because people move, people, don't respond to our efforts to track them, all those types of things. So the assumptions that go into cumulative incidence can be difficult to match, to meet. And we also assume that our population remains at risk. There's our at-risk term for the entire time period, right? So we put our at-risk population in our denominator from the beginning of our study. And again, we assume that they all have the potential to become a case. But the truth is, right, that potentially someone, say you're interested, again, in the incidence of ovarian cancer, so you're tracking all women and assuming they're at risk during the time, but there may be women who have their ovaries out for a reason that's unrelated to ovarian cancer. In theory, right, they should not be part of our denominator anymore because they are not at risk for the study period. But ascertaining those types of things is very difficult. So meeting that assumption can be difficult. So let's zoom into our example. So let's say we wanted to do a study where we tracked women receiving gynecological care through Temple. So we had a group of 5,600 women that we tracked through 2012. And over that period, that 1-year period, 345 received a new diagnosis of syphilis. So let's calculate the cumulative incidence of syphilis among women receiving gynecological care at Temple in 2012. So our definition of cumulative incidence, or our formula, is number of new cases divided by number of persons at risk at the start of the observation period, right? That's what we have above. So we can plug in our numbers. Here, our number of new cases is 345. Our number of persons at risk at the start of the observation period, 5,600. Just divide. We end up with a cumulative incidence of 0.062. Here we can multiply up, so we can end up with an incidence of 6.2%, or what you may see sometimes is incidence communicated in terms of 1,000 women, 1,000 persons, 100,000 persons, that type of thing. So in this case, and hopefully you guys can see that math going on, the cumulative incidence of syphilis among women receiving gynecological care at Temple in 2012 was 62 per 1,000 women, right? And so, in our first week, we talked about, well, why do we need to track health? So that's a really important number, right? So in 2012, we now know that 62 per 1,000 women receiving care at Temple were a new case of syphilis. If we had tracked that number over time, you may perhaps see that it's a decline over time or an increase over time. And those start to raise questions, what is driving this change? Do we need a change in services? Do we need some public health programming? Do we need policy changes, right? These numbers inform a lot of public health actions. So we talked a lot about the assumptions involved in cumulative incidence. What happens when you don't have a stationary population? What happens when you have people coming into your population as you're tracking them? And what happens if you have people that we call it lost to follow-up? So think about our fictional clinic population at our gynecological clinic. It's sort of unrealistic. It's very unrealistic to say, okay, we have 5,600 women on January 1, what was my year here, of 2012, and we have no new women, or we don't care about the new women coming in who may have started care on January 2nd, and that we actually know what happened to all these women, that they didn't receive a diagnosis elsewhere, or they didn't move, that type of thing. A lot of assumptions, especially for a population where it's probably not stationary. It's probably quite a dynamic population of women coming through Temple University clinics. So when we make assumptions about who's at risk, when we make assumptions that we have complete health information about our entire population over the period we study them and who got your disease, we are often wrong, right? If we assume that we've captured every diagnosis of syphilis, but we're missing a lot of cases of someone who left and got a diagnosis at another clinic, we're going to underestimate the incidence of syphilis among this population of women. So how do we solve that? We need to move on from cumulative incidence, and we need a calculation that takes into account how much time at risk each person contributed. Okay, so the bottom line is you'll see cumulative incidence a lot, but it holds a lot of assumptions, and it's really, in a lot of ways, too simplistic a measure. Although, to be honest with you, and a lot of times we can't get more detailed information, so that's why you see cumulative incidence. Okay, but what happens if you don't have a stationary population? What happens if you can't enumerate all of the cases in your population at risk? Then we need to move on and calculate incidence rates instead. So incidence rates is a slightly different definition. So as you'll see here, the numerator is the same as cumulative incidence, number of new cases. Then something different happens. The denominator is the total person time at risk. And you're probably thinking, what the heck do you mean by person time? That's just not a concept that's familiar to outside of epidemiology. So let's talk about it. Oh, I'll also say, remember way back when I talked about rates and how that rates, people often incorrectly use rates, but that rates need a unit of time in the denominator? Well, here's our time, and you'll see what I'm talking about. Okay, so what on earth is person time? So person time is the amount of time each person in the study was followed between when they started to be observed and then when they got the outcome or were lost. Okay, so it's the idea, in this sense, we have a stationary population on one side. You know, on day one of tracking people, we were able, in this case, I think I can zoom into this further, yep, to have 20 people that we're following. Okay, so, and in this case, we decide we want to follow people for 40 years. This would be, if we were just calculating cumulative incidence, it'd be crazy hard to track people and have complete data on everyone and know that everyone is at risk for the entire 40 years, right? So realistically, what happens to people? And in this case, the X's mean that they got the outcome of interest. The O's mean, excuse me, that they were lost at a certain point. And then if there's nothing and they've made it all the way to 40 years, that means they've contributed at-risk time for the entire 40 years. Okay, so let's go through this. So person one is in our study, we're following them, and then at year 30, they got our outcome. And they're no longer at risk, because remember, at risk means they have the potential to get our outcome. Once someone has gotten our outcome, they're not at risk anymore. So person one has contributed 30 years to our denominator, 30 years of person time. Person two stayed in our study for all 40 years and didn't develop the outcome. They contributed 40 years of person time to our observation, to our denominator. I'll just go through a few more. Person three was lost at year 20. We don't know what happened to them. We don't want to make assumptions that they remained at risk and didn't get our outcome, you know, between years 20 and 40 when we can't track them anymore. So we'll say that person three only contributed 20 years of at-risk person time. Okay, so when we're calculating our denominator, what we do across our 20 subjects is we add things up. How much person time at risk did each one of our subjects contribute to our denominator? And, you know, here this is only 20 people, so you could by hand calculate, okay, well that person was 30 years and this person was 40 years and this person was 20 years. But obviously, realistically, our computer programs do this. But this is the idea of person time at risk, that when we have a dynamic population on this end and we're losing people and we can't make assumptions that they're remaining at risk and didn't get our outcome, they only contribute as much time to our denominator as we know about them. We know they remained at risk. Okay, so this, a lot of people have a little trouble with this. They're a little uneasy. I would recommend if you're not getting it, I also have a complimentary other video that's going to be posted where I go through and calculate person time. But please let me know if you feel uneasy about this one. Okay, so now that we've handled on person time, let's move over to our example, and hopefully this will become crystal clear. So here we're returning to our group of 5,600 women receiving gynecological care through Temple. And here we're going to do the study slightly differently. So when we were calculating cumulative incidence, all we needed to know was the number of women in our population that we were following over time, and then the number of incident cases over that 1 year. Here, because we're calculating person time and we want to be more specific about how much at-risk time each woman contributed, we're going to assess the women for STDs every 3 months for 1 year. So in this example, we have 5,600 women. We've assessed them every 3 months for 1 year. And over that time, these 5,600 women contributed 60,200 person months. All right, so let's go back for a second. If our 5,600 women had been in the study for 1 year and they were all at risk for that 1 year, and then, just for sake of the example, all were diagnosed with syphilis on the last day of the year, they would contribute 5,600 times 12 person months at risk over that study. Now, that didn't happen in this study for a few reasons. First of all, we know we tested them every 3 months. So at every 3 months, there was a point at which we could say, okay, that person is still in our study and is still at risk. Let them keep going. Another option is that we could say that they've now been diagnosed with syphilis and they've stopped contributing person time after that 3-month period. Or the alternative is that they were lost to follow-up somewhere within that 3-month period. And so we don't want them contributing person time during a period at which we don't know that they remained at risk. So excuse me, this 60,200 is less than the person time that this cohort of 5,600 women would have contributed if they had all been at risk and followed for the entire 12 months. So among this 60,200 person months, and in this study, 325 women received a new diagnosis of syphilis during the year. All right, so let's go on to our formula. So our numerator for incidence rate is the same as it was for cumulative incidence, the number of new cases. And again, we still have 325 new cases. Our denominator is what changes. So here, instead of our population at risk in the beginning of the observation period, we're going to have our denominator be the person time at risk over the time period. So how much person time did these 5,600 women contribute over 1 year? So we're plugging in our 60,200. Then we can simply do division, and we end up with an incidence rate of 0.0054 per person month. All right, well, what that person per person month is very difficult to interpret, so let's unpack this a little. So we know that there are 12 months in a year, so we can multiply up and end up with, instead of person months, person years. So we can multiply our 0.0054 by 12, and we end up with 0.064 per person year. We can also unpack that a little further to get to a point where it's something that people understand. So we can multiply this by 1,000 and end up with, we had 64 cases of syphilis per 1,000 persons per year. That's actually understandable, right? So over a 1-year period, per every 1,000 person, we ended up with 64 cases of syphilis. We could also divide this out differently, potentially, and say we had 64 cases of syphilis per 100 persons per 10 years. See, we're unpacking that 1,000. There are a lot of different ways you can do it. I think that it usually comes down to what is most understandable to your audience. And I think in this case, because we did track the women over a year, so we could feel confident that we understand what happens in a year's time, it makes sense to report 64 per 1,000 persons per year. So let's just compare. We have our same 325 cases in our other example. Let me go back to this. But now we've more accurately accounted for the time that the women are contributing. So when we couldn't calculate the person time at risk that the women contributed to the study, we ended up with an incidence of 62 cases of syphilis per 1,000 women. Now, when we are more accurate and don't make a lot of assumptions about how long we've tracked the women and if they still remain at risk, we end up with 64 cases of syphilis per 1,000 per year. So not extremely different, but the incidence rate, when you can more precisely calculate how much time at risk these participants contributed to the denominator, you're going to get a more precise estimate of incidence. So if there's ever a case where you can track person time and do regular follow-up assessments and identify very specifically when they got your health outcome, you want to be able to calculate incidence rate. Okay, so those are our two types of incidents, and there are more examples in the short videos and in your lab assignment this week. Let's just talk briefly in conclusion about the relationship between prevalence and incidence, and we referred to this a little when we were talking about factors that affect prevalence. So prevalence, which again is our snapshot of time, who has the outcome either right now or over this period, prevalence is a mixture of two types of individuals. It's people who have the disease before the time period when you're observing, right? So again, they could have gotten something a year ago, but if you're collecting data over a week, they're counted. And then people who get sick during your observation period. So again, if you're sort of surveying Temple students over a week and they get sick on Wednesday, they're a new case, they're included in your prevalence. So prevalence is both old and new cases. And for this reason, prevalence is affected by both the incidence, so the number of new cases coming in, as well as how long the disease lasts. And remember, we talked about this with prevalence, that when we have really long-lasting diseases, when we do our snapshot in time assessment of how many people have disease, you're going to pick up on more people because there's just more people around who are sick. So the two factors are related, and this is the image that helps me think the most about the relationship between prevalence and incidence. So we can consider incidence as a waterfall, right? It's the number of new cases, it's the amount of new water rushing in to our pond here, or lake, or whatever body of water you want this to be. And this is our prevalence, right? So as the incidence increases, let's say there's a huge rainstorm and this waterfall is completely overflowing, your prevalence is going to increase. So as incidence increases, prevalence increases in response. Now, what then matters to affect prevalence is how long the people stay in that pond, how long the water stays in that pond, the duration of staying sick. So say, there's another waterfall and the people are able to flow out really quickly from this pond. They're able to they come in, they get sick at a certain rate, they exist in this pond, but then they're able to be treated. I'm mixing my metaphors and hopefully you're following me. So our prevalence is going to then decrease by this treatment, by this water coming out of the pond. And you might actually, eventually, right, have this steady state where you have new cases coming in and then cases being treated, and then your prevalence is going to remain level. But hopefully, through my convoluted example here, you can see that the prevalence, that amount of water in your pond is affected by the new water coming in, the incidence, and the amount of time water then stays in your pond. Okay, so here's a good example that may be more useful to you than the pond analogy. So here's looking at trends over time in HIV. And as you can see, we have actually a fairly steady state over this period of new HIV infections. But what's happening here, so this is HIV incidence, new infections. But what's happening here is that actually our treatment is getting better and people are living with HIV. So people aren't dying, they're staying sick with HIV. So when we ascertain prevalence, we do our point in time, do you have HIV, our numbers are going to go up. And it's not because there's that many new cases. It's not like all of a sudden there's another outbreak, due to some infection source. It's that people are actually living longer. So our prevalence increases due to new treatment options while our incidence remains stable. And again, we talked about this earlier with what affects prevalence. It's critical that public health scholars and practitioners understand what goes into prevalence, and that just seeing an increase in prevalence, it may actually be a good sign because it may mean that people aren't dying. There's a lot of factors that go into that calculation. Okay, so mortality statistics is for week 3. We're not going to go into that right now, but thank you and have a great week.